For hundreds of years, physicists, mathematicians, and engineers have been trying to model the world around us. Through observations, they have found a variety of properties that can be modeled using vectors, from mechanical forces to computer graphics to magnetism. Let's step inside the classroom to learn some more. An n-dimensional vector, which we can write as, for example, A, has n components. So each subscript here for A designates a component. This right here is an n-dimensional vector, and generally we consider vectors n-dimensional when we don't necessarily know. Say, for example, A is actually a two-dimensional vector. Let's say it's the vector 3, 4. Well, we can define what each one of these coordinates stands for. So let's say we say the first coordinate stands for the x direction, and the second coordinate stands for the y direction. Then we might have, from our starting point, we might have 3 horizontally and 4 vertically, which would mean A is this vector, which we draw with an arrow at the end. But because we define it this way, we don't necessarily have to. Each one of these coordinates actually could stand for anything, from variables in a search engine to coordinates in an n-dimensional space. So one thing that is important to note about vectors is they have a direction and a magnitude, but they don't necessarily have a location. So for example, this vector, say W, is the same as this vector W, even though it's been transposed. Think of forces, for example. The same force can be applied here or here. And just like the forces are equal, the vectors describing those forces are equal. But the effect of those vectors can be different depending on where they're applied. However, in many physical situations, we actually oftentimes put constraints on where we apply the vectors to. For example, if we have a box and we apply vector W here on the box, it will only pull it. However, if we apply vector W here, it will not only pull it, but also torque it so that it rotates. Another aspect that's important to know for vectors as we move forward is the magnitude or norm of the vector. So let's say vector A was 3, 4, as before. The norm or magnitude we designate by 2 bars on each side. And the normal Euclidean norm, we take the square root of the sum of the squares of all of the components, giving us a1 squared plus a2 squared. So you take each of the components squared and then sum. So in this, that's a1 and that's a2. So in this situation, we have the square root of 3 squared plus 4 squared, which is just square root of 5 squared, which is 5. So in this case, the magnitude of A is 5.
Vector functions are one of my favorite and most useful tools in my mathematical toolbox. You can use them to model fluid flows or even optimize search engines. I hope you enjoy learning about the vector functions that we cover in this jolt, and know that practice of these vector functions is the only path to mastery. I recommend creating your own vectors and playing around with these functions.